Hi, this is Guy Lapin from the University of Montreal and from the Rally Lab. I'm very sorry that I cannot be with you. And now, here is my contribution to this workshop. Hi, this is my contribution to the surface realization workshop, which is realizing universal dependency structure using a symbolic approach. So the idea is to first develop a symbolic realizer for standard universal dependency structure, then transform this universal dependency to an intermediary form, and this intermediary form will be rendered in English using an existing realizer that I've been working on for the past few years. And then I adapt this symbolic realizer for the two tasks of this workshop. So, as I've been working in symbolic AI for many years, I was curious to see how those techniques would fare in the context of tasks that have been designed mainly for machine learning techniques. So, just a recap of the format that we've been working on. So, I start from the standard dependencies, which can be seen either as dependencies or as a tree. And given this information, you might imagine a list of possible uh, universal dependencies realizer. First, of course, there's the trivial. If you have the full universal dependencies, you just have to take the second column and then you have all the words. But that's not really challenging. Another method would be to start from the tree of the that is given by the universal dependency structure and do an in order traversal of the tree. And this can be done in a 10-line Python program, which I would call 10-line baseline. But what I did, in fact, was more interesting is to do a real realizer that is using only lemmas and the tree structure information. So, in fact, many of the things that are given in the training data are not used. In fact, we don't use the forms, we don't use any of the position information that is given in there. Okay. So why would we want to do this? Well, first of all, it might be interesting if you could, in the context of a natural language generator, if you had a what to say modules that would generate UD dependencies, you could have the English uh, the English sentence output from this. Another use would be to detect annotation error because universal dependency structures are quite hard to build, even with editors and everything. But it is much more easy to see a bad dependencies when you see a bad sentence than trying to find a bad link. So this is the idea why I want to start from the the standard universal dependency notation. So first of all, I want to say what I will generate to. So the first thing is to use the existing generator that I've been working on, which is called GSRealB. This is a realizer written in JavaScript that is targeted to people who want to generate web pages, but it starts from a constituent syntax notation. That is, for example, if you have the standard the usual syntax notation, that is, you have a sentence in which you have a noun phrase, then a determiner, a noun, and this will be plural. And then you have a verb phrase in which you have a verb and then another noun phrase, and this verb will be to the past tense. So if you give this structure to GSRealB, it will generate women ate the red apple, in which you will see that this was done put to the plural, and then the verb agrees with the subject and so on. But what is more interesting is the fact that you can, starting from a single sentence, you can get many of them. And just by saying, for example, if you want to have this sentence negated to the passive and with a possibility, a model with modality possibility, then it will generate the red apple cannot be eaten by women. So this will be our target. So how we will do this? So for example, we start from the tree, so the usual tree, we parse it, and in fact the old system is written in Prolog. So we parse the universal dependency file, and then we create a Prolog structure in which you have exactly the same tree that is given by the input. And then the goal of the system, the hard part, is to go from the universal dependency to what I call deep syntactic representation, which is closely related to GSReal, but it's simpler to generate between this and this. And then finally, we use GSReal just to create his mother was killed also in the attack. Okay, so this will be the steps that we want to do. But the main step, the hard part, is going from 1 to 2. So first of all, how do we do this? So from a universal to the deep syntactic representation, we have to take care of morphology. So morphology, that is, we will map between the UD, the universal dependency feature, and the options that we have. So for example, if you have in universal dependency noun, mother, number, singular, this will be generated like that. If you have the verb be, the indicative, person, tree, so on, so you have more or less a direct mapping between those. The only problem is that we can the lemmatization in universal dependency is not always systematic. So it was a bit hard because in GSReal we expect that we have the base form here, but in the universal dependencies lemmatization is not always systematic. So we had to do some tricks to get around this. Then we have to go from the universal dependency structure to the deep syntactic representation. So essentially what we do is that we follow we more or less reverse engineer the UD annotation guide, in which we recursively build a list of deep syntactic representation labeled with the name of the relation, and the relation head is the constituent to which the dependents are added. If we look at the UD annotation guide, we have two types of dependents, that is nominal and clause. And the whole system takes about 100 lines of Prolog, so about 25 rules. So just to give you an idea, of the kind of rules that we have, we will look at, for example, for nominals, the triggers, what triggers a nominals is either a name, a proper name, an adjective, a pronoun, numbers, and the relation that are linked with nominals are the determiner, a mod, compound, and so on. So for example, if we look at this, for example, this in UD dependency will be mapped to something like that. And then if we look at noun here, then we see that noun mother possessive will be rendered as a noun. So we have written a list of a set of rules for nominals and other rules for clauses. So the same system, the same idea applies. That is, we have the verbs that triggers clause or preposition, and the relation are expletive and subj and so on. So for example, you can look at this. So for example, if you have killed and another part of the structure, you have add mod also, this will generate something like that. And as it is indicated in passive here, we have an auxiliary passive. We just had the fact that it is passive. And you also have the same thing, for example, in the attack. So it would be an oblique, and with the so so what we see that, for example, on a small example, this will generate, in fact, the same sentence that this is the example that I gave before, and this is the example that was used in the task description. Okay, so there is nothing we do really about it. People who are suggesting that we go out and fight them are living in dreamland. So it's quite good. It is only this because in fact, in the representation, it is not clear how we do the coordination here, and so the verb was not rightly didn't have the right agreement. So how does it work? So for example, we tested all the training data, so the 24,000 sentence of the training data, and you see that we get on the training data and on development data for all the English corpora. We only work in English, so we get about 50% of blue score. So now that we have that, we want to adapt it for the first task. So how do we do this? So the first task, the lemmatization, is already done by GS So this part of the T1 task is dealt with using, and the rest is word order. So what we do is that we build the tree, right? We do with the mixed line, but the tree, as the tree structure is more or less correct, then we sort the dependent on the relation name at each level. At each level, we start. Usually, we have one or two children at each level, and then the sorting is done on the relation name, and it is a given relation name. So a verb will always be after a subject, but before a complement, the determinant before an adjective, itself before a noun, and so on. So we took all the relation and we defined a global order, and we applied this at. So we more or less resort the tree, and then we apply the original UDSurfR on this. So for example, in the small previous example, this sorting gives exactly the same structure as the original one. Okay, so but it's not always like that, of course. And then for now, if we adapt it for T2, then what we did is more or less we did the same. That is, the documentation of the task gives a mapping between the names of the T1 relation and the ones of T2. So we just map the thing, the names of the T1 relation and the ones of the T2. So we build the tree and sort it on the T2 relation name. So for example, a subject with relation AI, complements with AI. In fact, the only statistical part that we do is that we apply more or less the most frequent preposition seen in the corpus, and then a subordinate is with A1 inv, and the compound name we had to do some tricks about the compound name. So for example, in our small example, so this is the T2 version of the small example that we had before. So given the T2 data, then we have the corresponding prologue representation, which is transformed into this, and it more or less give us exactly the same sentence as before. But of course, that's not always true. If we took a more complete, the more complex example, then of course it still works okay. So if you can see it, it is, we can do really in it nothing, and it's suggesting that we go out and fight. It's still understandable, but of course it's not so good. So how does this, what are the results for this? So if we took, if we apply this on the training and development data, then you see that we get more or less it's almost independent of the corpus, except for this one. But the blue scores are more or less the same, but a bit, of course, they are a bit less than the 4, but still quite acceptable. And for T2, they are also okay, but not so good, of course, because we have, they are missing quite a lot of information. Now, how does this system, this simple, relatively simple system, work on the real test? So, for example, this is the score. So our system is here, the first bar on the left, and we see that we are more or less, and those are the blue scores for the T1 test. So we see that we are more or less, we are not the best, but we are not the worst either. Okay, so this system, this is for T1, and this is for T2. T2 also, while there were quite less participants, so we see that except for this one, we are quite competitive. So this gives you an idea now for the human evaluation. Okay, so that was for the blue score. For the human evaluation, we see that this is the small star in the middle is the score that our system got, and which is not far from the, for example, for the grammaticality versus the average blue. So it gives you the relation is not so important between the two, and for grammaticality it's not so bad, because this is in fact the human. So human got for grammaticality about 70%, and this is the star here is the 10-line baseline. So you see that it is not so important, the difference between the two. And this is for T1, and for T2 for grammaticality, that's about the same pattern. And for T1, for the human evaluation on the meaning, we see that we have you see that the 10-line baseline is not so bad either. So all those systems, and our system is about in the middle also. So what can we conclude from this is that the symbolic approach is quite competitive for a system running on a small laptop. In fact, I ran all the test development and training test in 5 minutes on a laptop for all the tests and writing all the files. So, but what we can also see is that T1 is, in fact, in my opinion, quite too easy as a task, because and also it does not correspond to a real NLG task, because in fact it would be more interesting to, I can't imagine a system, an NLG system that would generate all the tokens but in the bad order. T1, T2 is more realistic, but very few teams tried it. And I think that our GSRealB is an interesting interlingua, but of course a statistical language model post-processing would help greatly. So, merci beaucoup.